Greetings, everybody. I'm Christopher Smith. I'm the advisor for SteamPost 26, and I am leading the session today on Java programming for FTC robotics. What we're going to focus on today is, and there's some things that we've done, some basic core knowledge that you kind of need to have in terms of Java. As far as the environment, having it set up, what you got to have is Android Studio. I'm going to assume that you've already taken care of that. If you've got any questions about the setup on that, just reach out to me and we'll help get that all set up. What we want to focus on today is we're building a library for Mecanum Drive. And this is going to get into a lot of concepts and share a lot of information. And this is the reason why I'm making this video, is because there's a lot of good stuff that I think that comes out of this process. And our goal here is, in autonomous mode, we want to be able to send a command in autonomous mode, tell the robot to go a particular direction, and then drive that heading, and basically strafe to it using Mecanum, the advantages of Mecanum wheels. And I've got a couple of sample Mecanum wheels right here. This is one that would go in the front of the robot, or in the left rear, so the right front, left rear. And then this is one that goes in the left front and right rear. So I've got these available just so I can reference them throughout this session. So what I want you to think about is, I want you to think about the dynamics of the robot, how it works, and then we'll go from there. Now, as part of our session, I need to do a little bit of base work on trigonometry. We're going to talk about trigonometry real quickly. And this is not a full trigonometry class, just some basic concepts to kind of help you understand what it is that we're programming as we go along. So I'm just going to start, and I'm going to jump right in here, and I'm going to give you some concepts, and then we're going to jump in, and then we're going to talk about how that applies to the robot itself. And then once we have that down, then the next thing we're going to do is we're going to talk about how to build the program. So we're actually going to build a library, and this is a separate library that then can be used by any autonomous mode application program to kind of streamline the development of the autonomous mode programs. So let's get started. First of all, we're going to jump in, and we're going to talk about a unit circle. And I believe you should be able to see that. So unit circle in trigonometry, I apologize, I'm not a brilliant writer, but the concept of a unit circle here is that I can build a triangle. Excuse me. I've got a circle on our axis. I got the y-axis, and I got the x-axis. Got a circle. The length of this circle is 1, just as a single unit, 1. And that's going to simplify some of the mathematics that we're going to do. And then this is going to be our y component, and this will be our x component. But let's not do that. Let's not think about it that way. What we want to think about this as this is the angle that we're focused on, and this is the opposite side of the triangle from that angle, and then the adjacent side is this guy right here. Now, again, this is not a complete trigonometry class. I'd encourage you guys, if you're not familiar with trigonometry, there's some great tutorials online. You can go and find a lot more detail about how this works. But just the concepts here, what's important. So I got this right triangle here. That's important because then that makes everything else kind of come together. So there's some functions, and I'm going to talk about a function for theta, and I'm going to call this function 1 of theta. And I'm going to say the function of theta, I'm just going to do a ratio, if you want to think about it that way, where the ratio is going to be, and I'm going to call this, for purposes that are going to come together pretty quickly, I'm going to call this a sine function. So I'm going to say sine of theta. And what this function is going to do is it's going to take the ratio of the opposite over, or divided by, the hypotenuse. And this is the hypotenuse right here. And in this case, it equals 1. So the function is sine of theta equals opposite over hypotenuse. Now, because hypotenuse equals 1, then really what we're saying is sine of theta in this particular special case equals the opposite value. So whatever this value is going up, that's what sine of theta is. So that's the function that we've created. Now, again, this will make more sense as we go along. We're going to create a second function, and we'll call it function 2 of theta. And this one we're going to call cosine. So cosine of theta. And if you're familiar with the way that cosine of theta works, this is very simple, but in this case, we're going to take the adjacent. So it's a ratio of the adjacent over the hypotenuse. And in this case, the hypotenuse is equal to 1. So what that means is the cosine of theta equals the adjacent value, okay? So where this is going to come into play here in just a little bit is it's going to help us create vectors and directions and doing what we want to do. Now, I think that's where I want to leave it in terms of trigonometry. These are the functions and the capabilities that we'll think about, and it will help us throughout this process as we move forward. But I really want to dive into the meat of the Mecanum wheels and the robots. So I'm going to slide this up here. Let's think about this a little bit differently, and let's put this together. And these are my wheels on my robot. So think about these as being Mecanum wheels, and I've got a rectangular robot here. Hopefully yours is a little bit more square than mine, but nonetheless. And so whenever you have Mecanum wheels, and the way I think about setting these up is that the Mecanum wheels, if you're looking at the top of the Mecanum wheel, and this is important, top of the Mecanum wheel, you're basically creating what I refer to as the X. Now, the reason why I look at the top of the Mecanum wheel is it's much easier to figure out what's going on when you're looking at the top of the robot, looking straight down. And I want to make sure that these wheels on top are this direction, okay? Now, it's important that you realize or understand that the direction it's going on top is going to be the opposite direction that it's on bottom. So when we look at this on bottom, we actually have our wheels, the bottom wheel that's on the ground is facing this direction. But if you're ever building a robot, you're putting Mecanum wheels on and you're trying to figure out, did you put the Mecanum wheels on correctly, looking at the top and just making sure this red X is here in place will help you quickly identify, did you do everything right? Okay, so that's the part that I want to make sure that you're thinking about, and we're getting that all correct. All right, so from there, once we got the robot built correctly, what we're going to think about is if I drive forward, I have a force vector that I apply to each wheel. Now, keep in mind that every one of these every one of these wheels has a motor on it. So they're independently driven. And I'm not an artist, but I just want to make sure you're thinking about this because this is important in terms of the way that you set this up. Now, one of the things you can think about is that this motor right here is flipped over from this motor. So they would actually spin different directions. When you build your hardware profile, you can programmatically tell this it actually is supposed to spin the other direction as its forward direction or as its reverse direction, depending on what you want to do. So these can be set, or the direction or rotation of the motors can be set in programming so that you apply positive power and the right side goes forward, and then the left side, because it's reversed, can be reversed in program so that it also goes forward and they move forward in the same direction. So we don't have to make any special adjustments in the code to account for the fact that the motors are physically flipped and facing different directions. So that's, we'll deal with that in the code. We won't worry about that here in our algorithms. So what we have here is, when we think about this, is we have vectors. And what we're looking for is, what is this vector that we're working through here? Now, as we're doing this, we have to control each one of these motors independently. So they're all going to have their own power that's being applied to them. So we have to calculate exactly how much power to apply to each one of them, depending on which direction we want to go. So first thing we need to do is we need to make sure that we absolutely are paying attention to how we're labeling these guys, because they're going to have different power. So this guy right here is the right front motor, because this is forward position. So I want to think about this as, and on some robots, you can have, your front or back can be almost, it's a flip of a coin to decide what you want to have be the front of your robot. You need to make the decision for autonomous so that you can control that. So if you have this is right front, then this is going to be left front, this is going to be left rear, and this is going to be right rear. Now, I intentionally went from the top, the right front robot, to the left front robot, to the left rear, to the right rear. I did that on purpose, and that's kind of the format I'm going to follow, because it kind of makes things look nice and clean here. So now that we've got that, what we want to do is we want to figure out, well, how much power do I apply to my right front motor? So let's figure out what this is going to be. Well, in this particular case, we're gonna focus on an angle, and I'm gonna cut through some stuff. I'm not gonna spend a lot of time on it, but I'm gonna say this is my angle here. I'm actually gonna make an adjustment of 90 degrees, and then I'm also gonna flip it. But and that's all gonna get done in code. I don't want you to worry about that. I just want you to think about this as it's being written out here. And so the way that we're doing this is, this vector, this direction is going to be, this is the adjacent. I don't know what this value is going to be. This is a big question mark. But I do know what this value of theta is going to be, the angle I want to go, the direction I want to go. I know that value. So knowing that value, what I can do is I can use my sine function that we created up here, and I can calculate what adjacent is. So the adjacent, I'm sorry, I'm doing that backwards. That is not adjacent, that is opposite. Let's make sure I get this right, because I don't want to create confusion. This is opposite. The sine function is the one we set up for opposite. So sine of theta equals the opposite, or in this case, we can call this v sub y. So v sub y equals theta, and I'm cleaning that up just a little bit, a little sloppy there. Do a better job of writing theta. So my vector in, my vector in the y direction is going to be sine theta, and this is the adjacent. My vector in the x direction, this guy right here, is going to be v sub x is going to be the cosine of theta. And theta is the only value that I know. I'm basically saying, here's my angle I want you to go, whatever direction it is, head off in that direction, and good luck, and I'll tell you when to stop. So then we'll have to figure out in code, at what point do we stop? But what we want to do is we want to make sure that we're going in the right direction here. So I'm gonna give you some quick calculations to show you how these values are figured out. So right front, what we want to do is we want to add the vector in the y direction with the vector in the x direction. And then the left front, we're actually, because we're working on the opposite side of the robot, there's a inverse function, or a, we're gonna make this a negative value. So it's v sub y minus the v sub x. And then from the left rear, we'll have v sub y plus v sub x, and then right rear is going to be v sub y minus v sub x. Okay, so that's how we calculate the value. And this assumes that the robot is not going to rotate. If you start rotating the robot, these calculations are off the table. So you're going to have to get more do a little bit more math to figure out at what angle or how quickly you're rotating. So we're going to assume that no rotation is occurring in these calculations here. Well, so what I want to do is I want to take my v sub x and v sub y and plug in my functions that I've created for these guys. And what we're going to do, because I don't know what v sub x or v sub y is, I only know what the heading is going to be. And this will make more sense as we go forward into the programming, I hope. So what we're going to do is we're going to say sine theta plus cosine theta. And this is what going to be our f right front value, is this function right here. So this is what we're going to need for our calculation. And then we're going to say for left front is going to be sine theta minus cosine theta. And I'm going to put these in parentheses just because I'm treating it as a function. I'm going to think about it like a function. So this is my left front right here, and this is the calculation I'm using for the left front. Then we're going to go to left rear, and this is going to be sine theta. That's a terrible theta. Let's try that again. Theta plus cosine theta. And then that's that function. And then our right rear function is going to be sine theta minus cosine theta. Okay, and that's right rear here, and this is the function associated with this. So there's a couple of other points I want to address before we go in and jump into the code and start coding this. The first point I want to address is that the positioning, I told you that I'm making this adjustment for my starting angle. If you were to say sine of 0 degrees, what you're going to get is sine of 0 degrees is going to be 0, because a sine wave looks like this. Let me just real quickly create a sine wave, and it looks like this, right? So your sine wave is going to continue out. This essentially is the 0 degree point, and then this is going to be 90 degrees, and this will be, I'm sorry, that's 180 degrees. Back up here. This is my 180 degree point, and then this is my 90 degree point. So oh crumb, I got that wrong again. Let me make sure I get this right. Stay in school, kids. This is 180 degrees. This is 360 degrees. This right here is your 90 degree point, and this is going to be your 270 degrees. So what you get is your sine wave is going to be 0, or your sine value for sine is going to be 0 at 90 degrees, or I'm sorry, 0 degrees. And what we want is at 90 degrees, our heading, we're going to make an adjustment. So our heading at 0 degrees is actually going to be facing not at the 0 degree point, but it's actually going to be at 90 degrees. So we're going to work with that, and then we're going to make an adjustment on the angle that we're working from. So what I want you to think about is, as we do our coding, our angle theta that we're going to be using is going to be our heading. So let me just put this in. Our angle theta is going to be our heading plus 90 degrees. Okay. And then one of the things that we'll do in terms of the calculations inside of Java is we're going to do this in radians. We're not going to do this in degrees, just because the functions are better suited for radians than degrees. Okay, so with that, and this kind of gets us the math and all of the stuff that we're working with. We're gonna move this aside for now, and I'll pull this back up if we need it. But I'm gonna move this aside for now, and we're going to now focus on our programming. So let's go over here and let's take a real quick look at what we got. we previously built a hardware profile, and we'll have that posted so that you can grab that hardware profile and work with it. It's very simplistic at this point in time. What we want to do is we want to come over here to libraries. We're going to create a new Java class. And this new Java class that we're going to create, for now, we're just going to call it robot correct. I'm sorry, actually, let me do this differently. Let me call it drive Mecanum, like this, okay? So drive Mecanum is going to be our drive class. And this is where we're going to start from. So the first thing we need to do is we need to import some libraries or packages. So we're going to import com.qualcomm.robotcore.eventloop.opmode.linear.opmode, okay? And let's go with that for now. That's all we need to get started. And so what we're going to do is we're going to have to create some our hardware profile or our robot. So in the hardware profile over here that's already been created, right here, we have defined the robot. What we're going to do is we're going to create an object for that robot. So let's do private hardware profile, and you'll see where it's automatically up here imported our hardware profile, which is great. So we didn't have to do that. And we're going to create our object, and we're going to call it robot. Okay. And then we're going to create our. So we talked about the motors, the positions. So we're going to create some variables to house to hold the values of the calculations that we're going to create here. So we'll do public. We're going to make these double, and we're going to do. And I want to start the way that we had this worked out in our program. So we started with, right front, left rear, right rear. Okay. And then we're also going to create an op mode. So we'll do make this public. And we want this to be linear op mode, which you see that we've already imported that. And we're just going to call this op mode. Okay. So then here we want to, I'm just going to comment this, I'm not going to do too much commenting throughout this tutorial, but what I encourage you to do is comment stuff as you go along. But we're going to do a constructor method. Now, if we didn't include this, Java will automatically do it, but I prefer to include it. And we're going to actually, there is a function we're doing here. So this will be part of our initialization. We'll need this in our case. So we're going to do hardware profile, my robot. It's just a, whatever robot's being passed in, we're going to take it and assign it, and we're going to do linear op mode, and we're going to use my op mode. Okay. And so we'll do robot equals, and we define robot above. And we're going to say this equals my robot that gets passed in. And then we're also going to do op mode equals my op mode. And that's our constructor. And one of the things I do from a programming perspective, because you can lose track of squigglies pretty easily, squiggly brackets, I prefer to go in and just say this closes the drive Mecanum constructor method, so I don't accidentally lose track of that guy. So now what we're going to do is we're going to create a function. We'll do this public void, and this is going to be the robot correct. So this is going to be the algorithm that is going to apply the power to each of the wheels, and if it veers off course, if it sways, if we have any sway or yaw, then what it's going to do is it's going to make some adjustments to the power levels as we go along here. And we'll talk more about that as we'll come back to the whiteboard to get into that. So what we need is we want the programmer from the autonomous mode program to be able to send us some variables. We want to know, first of all, how much power, because we're not going to assume full power all the time. We don't want to just assume what the power should be. We'll let the programmer send the power value. Next thing is the heading. What direction do you want to go? So remember, the robot's not going to be turning in this case. If we could create another function that actually causes the robot to turn. This particular function is simply going to move it around and strafe in whatever direction they want to go. So we'll need a heading value to know which direction they want to go. And there's many different ways that you can control how far you go, distance. For now, we're going to do this by time. And just because time is a simple way for us to do this, we'll need to add some sensors to our robot to be able to use different methodologies. But you could do range sensors. You could do it until you hit a color sensor. You could use odometry if you wanted to. There's different ways that you can do this. You can, if you're using Vuforia and the images on the side of the wall, then you can maybe drive till you get to a certain distance, or from the pictures or whatever. We're not going to worry too much about that, but we are going to have that here. So I'm going to do this as a close robot correct method, and I've done this. I do this because I've messed up so many so many different programs and tried to troubleshoot, and it's just been out of place squiggly. So there's a couple of things I'm going to add here we're going to build in some troubleshooting as we go along. So this will make some more sense as we get further into it, but I'm going to add a string action is what I'm going to call it, and let's set this equal to initialization or initializing, right? And what this action is we can create a separate function that prints out our parameters, the current values of our parameters, but we may want to know, well, I see the values of the parameters coming. I want to know what action I was taking whenever those parameters came up. So that's what this is going to be. We'll pass this information along to a method that we're going to create here in just a minute that's going to print everything to the screen. So then we want double, and we're going to get init z, and this is going to basically be our function that is going to, or our variable that's going to hold the value of the gyro sensor. So we're going to pull the gyro sensor value. And in fact, let's initialize with the method called get z angle. Now, we don't have this method yet, so let's just take a break down here and go create this method. It's a very simple method. We could just put this in without creating a method. What I found though is that if you end up changing your sensors, you want to do something different with the way the value is being collected, then you run into a lot of problems if you broke it up and you just put the command in individually. So what we're going to do is we're going to create a method, and that way if we ever change the methodology by which we're getting that gyro sensor value, we can come right here and adjust the method that we're using. So we'll do double. So we're going to return a double value, and then we're doing get z angle is the name of the method. And then this is going to be really simple. Like I said, we could have done this on the line without doing anything, but we're going to do robot.imu, and that's where the gyro sensor value is going to come from. Get angular orientation dot first angle. Okay. Now, I'm not going to go into a whole lot of detail as to the functions that are built into the IMU right now. That actually would be a great opportunity for a follow-up session. But what we'll do right now is I want you to know this is going to pull the angle that we're interested in, and I want you to notice that I made this a negative value. And what I found is that this just simplifies the way that I think about this. This isn't the only way you could do this. You could do this differently, but when I told you that we were going to make an adjustment of 90 degrees on our starting angle, and then we're going to flip everything for heading, this is one of the reasons, the way that I do this It works better in my head to do it backwards, but you don't have to do it this way. You could actually go adjust the math and do it without making this adjustment. So I apologize if that comes off as confusing, but it may be confusing in some sense until you get used to it. But as we go through here, hopefully it'll all make sense. So we initialized our gyro sensor value. That's the init z. So the next thing we want to get is we want to get at some point in the program, we want to get what the current z value is. So we'll grab that. We can set it equal to 0, but let's create a variable for it. And then with the initialized z value, we're constantly going to be comparing it to the current value, what the current reading is. And so as we do that, we'll make a correction, make an adjustment, one way or the other on how we want to drive forward. So we need a value, a variable for the correction. So we'll do a z correction, and we're going to set this equal to 0 as well. And by the way, we could put these on the same line if we wanted to, separated by commas, but I'm going to separate them out so that we can just talk through them. The next thing I'm going to do is I'm going to do a Boolean, and this is kind of laziness on my part. This is just going to be we'll do a check to see how much time has expired if we've exceeded the duration, and we'll change our active value to false once we either equal or exceed the duration. So something we'll watch out for. So then the next thing next variable we're going to define is theta. We'll just call it theta. And theta is going to equal, so I told you we're going to do this in radians. So what we're going to do is we're going to call in a math function. And the math function we're going to do is 2 radians. So it's going to do a conversion of our heading into radians. Now I'm going to separate these with spaces just because I like to have a little bit easier to read. So we have 90 degrees plus the heading that we're going to be following. And finally, the last thing we're going to do is we're going to add a new method called elapsed time. Now I'm going to point this up here. It's not a method, an object called elapsed time. The elapsed time package was pulled in, or the class was pulled in, so we have access to that. I want to call this runtime. So we're just going to keep track of our runtime as we go through here. And so this is going to be new elapsed time. Okay. So those are all of our variables that we're going to be concerned about right now. So the next thing we're going to do is we're going to say if runtime dot time is greater than or equal to duration, then we want to set active equal to false. Okay. Now you'll notice that active is kind of grayed out here, but it's all good. All right, so then the next thing that we're going to do is, and I'm going to build in some troubleshooting capabilities into this, because anytime you do this type of programming, you're almost always going to run into problems, and you're going to need to see values and variables. So before we do that, let's jump down here. So let me clean this up just a bit. We're going to add, this is our method, get z angle. Okay. And then let's come down here and comment this. Just make a comment here as close get z angle method. That's just for me. So again, in the future, whenever I'm coding and I lose track of those squigglies, we're all good. So what we want to do now is we're going to create a new method here, and this one's going to be do public void, and I'm going to call it update values UES, and we're going to go ahead and pass in some information here, and I'm just going to tell you what information I want. So the first thing we're going to do is I describe the action. That, you know, we want to know what action we're going through and when we're looking at the values that are being printed on the screen. So I want to make sure that's there. Let's look at the initialized value of Z. And this is important in case, as we're running through the program, something gets changed and then we have a different value of Z. We want to know what we're comparing our values to. So let's look at our double init Z. And then we're going to do, let's also throw theta in there. So we'll print theta out onto our screen. It'll be helpful to know what the current Z is, what that's measuring out to be. And then also we want to know what the Z correction is. And that, the reason I just want to print these on the screen for us so that whenever we're doing troubleshooting, it's easy to look at those values and see what we're getting. So let's break this up and let's take a look at this. So we're going to do telemetry, and we're going to do add data. And the first data that we're going to add is current action equals, and then we're going to put in action here. Oops, forgot my, there we go. And then, you know, we can just copy this. That way you don't have to put so much in there. And then the next thing we're going to do is we're going to do our init Z value. And then let's just do init Z. And then we're going to do, the next one is going to be theta. And remember that theta will be adjusted by 90 degrees. We'll put theta in here. And then we're going to do, the next one is going to be the current Z value. Do current Z. And the next one, last one we're going to do here is the Z correction value. And this will just help, you know, as we're troubleshooting, we'll see if anything is out of kilter. Now, in addition to that, I want to add some our values for our wheels, what's happening with our wheels. So let's also add in right front, make sure I do them in the right order. And this is going to be right front. I could do this as, yeah, it doesn't matter, that's fine. All right, we're going to take this as left front. This will be LF. Okay. And then we're going to do, let me just put the other two in here. We'll do left rear. And then we'll do right rear. So now, again, we're trying to keep those in the same order so that whenever we're looking at the values on the screen, they match up with the way that clockwise orientation that we walk through. Now, if you prefer a different orientation, you can put them in differently. That's totally cool. Now that just puts all of the telemetry data into, you know, gets it ready to be printed. We actually have to tell it to print to the screen. So we'll do telemetry dot update data, or just update. And that should be that. Okay, so now again, let's add in close update values method, so I don't lose track of that in the future. Now what we can do is we can take this update values and in here, I'm going to go ahead and print that to the screen so that if, as we're looking at it to initially, we've got some values. So update values, and we're going to, it's looking for action, which we predefined. It's looking for init Z, which is going to be whatever the current initialized Z value is. Theta, current Z, which should be 0, and then Z correction, which should also be 0. So those should be the things that we want to see on the screen to begin with, okay? So now the next thing we want to do is we want to create a while loop. In a debate about whether we wanted to create calculations for the wheels here or do the while loop, let's do the while loop, and this is the way we're going to do it. So we're going to say while, and I'm going to check op mode, and then op mode is active. So I want to make sure that the op mode is active, but I also want to make sure that our Boolean value, this guy right here, active is true. So we could put a quick check in here to see if we actually are less than the duration. Like if somebody were to pass a negative number, then we wouldn't even go through this. It would just skip right over it. But let's assume, you know, it's not necessary. So the first thing we want to do is we want to do a calculation on our values here. So let's start with right front, and you'll recall that right front equals the basically we're gonna do the power factor here, and we're gonna say power times, and then what we're gonna do is we're gonna say sine of theta plus cosine, and I'll come back and fix these theta. I'm just writing it out pretty much how we had it in our program or on our whiteboard session. And we got to do some math here. So this is going to be a math dot function. And so then that should be sine. You'll notice that that cleared up. And then we're going to do math dot cosine. So that should clear up too. Okay. So I put the outside parentheses here, and I put, so we can multiply by our power factor. Power factor is being passed in. So if I say 10% power, 20% power, 50% power, will automatically increase the value. But now what we've got is we've got our calculation here. And now that we've got that, let's just copy that, because the reality is these should be pretty straightforward. So we got right front. Well, let's do left front. And then we're going to have left rear. And then we're going to have right rear. Okay. And by the way, you'll recall that left rear is minus cosine, and so is right rear. Okay. So now we have, theoretically, if we just applied a power and a heading, this actually should work, right? In a duration. Well, the duration won't work because we're not checking the duration. So why don't we do that real quickly? Right. So what we can do here is we can say if, and we're going to look for runtime is greater than or equal to duration, then active equals false, right? So there you have it. Now, theoretically, as long as you don't put in an infinite duration, which you can't do, but a massive duration, this whole function right here should get us driving, and get us going in the right direction at the right power. And we could actually test this real quickly if we wanted to, but I'm not going to do that now because I want to make sure that we have all of this together and everything is working. So the next thing we're going to do is now we're going to start doing our correction. So what we've got to do is we've got to consider various scenarios and what could potentially be happening in the scenarios. Okay. So let's do this. We're going to, now you notice I haven't applied any power to any of the wheels. I've only done the calculation. So I said this would work. I was wrong. One of the things we need to do is go ahead and add the power to the wheels. So let's just let's go ahead and do that so that this would be something that would work. So I told you it would work. If we had tested it, I know we would have failed because we're not applying power to the wheels. So let's do that. So I'm going to do a real quick comment here. And in this one, what we're going to do is we're going to say robot.motor, and we want to do right front dot set power, and we're going to set right front value. We're going to do robot.motor left front set power, and we'll set left front. We're going to do robot.motor left rear set power left rear. We're going to do robot.motor right rear. Right rear. Okay. So now, theoretically, it should work. Again, we're not gonna test it to see, but what we do know is that if it got bumped, it's going to now be bumped off course to wherever it's going to go, because we're not making any adjustments to the way that it's behaving. It's just going to continue to rotate through. And you'll notice that what's going to happen here is that it's going to set the power, it's going to check the time, then it's going to apply the power, then it's going to go back up to the top. And if you hit stop, this op mode is active, is going to be false, it'll kick out if you hit stop on the phone. If you didn't hit stop, but we've gone over the time duration, then it will kick out. And one of the things that we should do is we should do a function down here that tells the motors to stop. So what we'd want to do is robot dot, and what I'm going to do is let's just create this as a method, right? So hang on, forgot to do my comment on this one. So let's add the comment here. This is how I like to do my comments. This is method. Update values, and a lot of times I'll come back in here and add the value information so that this stuff is all documented. If you're just looking at the method itself, you know exactly what values are being expected. But we're not going to worry about that right now. I've got a placeholder for it. So what we're going to do is we're going to add another method here. This method is going to be and what we're going to do, call this motors halt. And all this is just going to tell the motors to stop. So we'll do public void motors, or motors halt, HALT. And inside this guy, let's just go ahead and say end of motors halt method. And what we're going to do here is we're just going to say robot.motor, and let's do them in order. So right front dot set power equal to 0. Robot dot motor left front dot set power equal to 0. Robot dot motor left rear dot set power equal to 0. And then the last one, robot dot motor dot right rear dot set power equal to 0. And so now, rather than typing that out every time we want to stop the robot, we just come up here and we say motors halt, and we're done with that. So dropping out of that, that will stop the motors, because what would happen here is if we left this going, these motors still have power on them, and we haven't told them to stop without doing this motors halt function. So we can move into the next function. If they're not applying the powers to the motor, that the robot's going to continue to go. So this is an important step right here to shut those motors off. So you notice right here, I didn't identify what this is. Let's go ahead and do that, because I was looking at it going, huh, I wonder what that goes to. Now you can follow the line and figure it out, but you know what, I just notate it. All right, so now what we're going to do is we're going to apply our correction. Now we could do this in a couple of different ways, but we set these values right here. What we want to do is we want to look at our gyro sensor value and see if anything has changed, if it's adjusted one direction or the other. And if so, then we want to go ahead and make some modifications. And there's a number of different special cases for this. So driving forward is a special case, driving backward is a special case, driving 90 degrees, well, that's not a special case, but it is a case, a use case that we have to factor in. And so anything to our right, anything to our left, and those may be all of the special cases that we need to be concerned about. So what we're going to do is we're going to make sure we address each of those special cases and you know, add in a correction value to each one of them before we actually set the power to the motors themselves. So first thing we need to do is we need to get our current Z value. And by the way, we made a function for this, and you'll recall that we used that function right here. It was the get Z angle. We ran that function at the very beginning to get an initialized value. We don't want to change that initialized value because we want to compare to what the starting value was to what our current value is. So if that's changing, then that becomes a problem. Okay. So now the next thing we want to do is we want to compare and see if there's a difference between the current Z value and the initialized value. So so we'll do this. We'll just say if current Z is not equal to init Z, the initialized Z, then this is what we're going to do. So now one of the things, I'm going to copy this because I want to put a comment here so I don't lose track of this. End of if, and then I'm going to just, oops, did not mean to do that. Then I'm just going to paste this in here. And so I know which if statement that is because we're probably going to end up with a bunch of if statements in this process. So let's think about this. If they're not equal, then we need to adjust our Z correction value. So we've got a variable set aside up here that is our Z correction value. So let's go ahead and put a value in there so that we can use that to make adjustments. So the way that we're going to do Z correction is we're going to say Z correction equals the difference between the init Z and the current Z. Now, the way that we actually want to look at this is we want to know this correction value that we're doing, we want to know if it's positive or negative. And so what we're going to do is we're going to say, let's make this always positive. So my correction value, the Z correction, is always going to be positive. So if I need to adjust negatively or positively, I can just do that in my calculations down below. And I don't have to worry about, well, did the Z correction number get changed? I'm going to make those adjustments as we go. Now, you don't have to do it this way. You can do it other ways, but this is the way we're going to do it. We're going to do math.absolute value, and we'll do the absolute value of that function, right? So that's going to give us a positive value, and then we'll do a set each power calculation on each of the wheels the way that we want to set them. So then the next thing we need to look at is, so I told you the different cases. We've got forward and backwards. Let's hold off on those, and let's think about right and left to begin with. So let's do this. So let's think about what the heading is supposed to be. If the heading is greater than 180 degrees, so what we want to do is, and we're thinking about my left hemisphere here. So if the heading is greater than 180 degrees, but if it goes over, so we want to do a range of 180 degrees up to 360 degrees. And I'm going to say, let's not do it at 360 degrees because that is the same use case as 0 degrees. And 0 degrees adjustment is actually kind of a special case, and we'll talk about that later. But so let's confine this to between heading is between 180 degrees and less than, so let me say, and heading is less than 359.99999 degrees. Okay, I want to get as close to 360 degrees as I can without actually being 360 degrees. Okay, that's what I'm going to do in this particular case. Now, I could probably join those two together, but I'm going to leave them at this point right here. So I'm going to copy this. I'm going to say, just put in my end of if and that one, so I don't get these mixed up, because you can see how easy it would be to get them mixed up. And now what we want to think about is which way are we actually veering off course. So let me grab my whiteboard here and my iPad, and I'm going to have to connect this back up here. So give me just a second here. Should take a second. Okay, there we go. So let's think about this for just a minute. I'm going to draw this out because here's the problem that we're trying to solve. I want to make sure it's clear what problem we're trying to solve. And let's not do that in red. Let's just do this in black in case I want to highlight something in red. So I've got my robot, got my Mecanum wheels like this. And let's say for this particular exercise that, and what we're looking at is this left hemisphere to start with. We could start anywhere, but I'm going to do this one first. And what we're going to focus on is, let's say this is strafing this direction, general direction, and something is happening so that it is veering either this direction and wants to strafe, maybe if I were to do this in red here, maybe it's trying to rotate ever so slightly like this and go this direction, and maybe it's going to keep going, keep rotating in that direction. What we want to do is we want to do a course correction and make it come back so that it is now, oh my goodness, so make it come back so that it is now back in alignment with our original orientation, but move further over this direction. So it's staying on course. That's what we're trying to do here, is just make sure if it goes the wrong direction. And then we're also going to, consider the case where, let's say maybe it's coming off this direction and it's starting to veer this way, right? I'm exaggerating these, and we want to do a course correction that direction. Okay, so this is what's happening potentially with the robot as it's moving to the left, and it could be moving to the left in any direction, right? I want to keep it in its orientation so that it ends up exactly where I expect it to be as I'm going that direction. So we'll control the orientation as it goes across, okay? So what we're going to think about is our Z value. So I'm going to set this over. We're going to compare our current Z value to the initial Z value. So let's do this. So if the current Z is, in the first case we'll look at, is greater than the init Z, then let me grab this. I'm just going to say end of if and this one. Okay. So what we're going to do here is we're going to change the value for the right front, and we're basically going to take the right front value, and we're either going to add or subtract our correction value. And by the way, one of the things that I want to do here, so we have our correction value right here. Let's do this. Let's adjust because the correction value is going to be an absolute value, but it could be 1, 2, 3, 4, 5, and that's going to be too big to use as a correction value. So what we want to do is we want to divide this by 100 and make it like 1% of the value, and we'll just do very short, small corrections. So let's add that in here. So what we're going to do is we're going to take our right front and we're going to add our Z correction. And that's all we got to do is that we're either adding a little bit more power to a wheel or we're reducing the power from the wheel. For the left front is going to equal left front minus the Z correction. And then the left rear is going to equal left rear plus Z correction. And then right rear it's going to equal right rear minus Z correction. So, and what's happening there is that, let me see before my iPad goes to sleep here. Let me bring this back over here and let's think about this just real quickly. Just so you have some train of thought on this. So let me redraw this because it's getting a little messy here. I have all that stuff on there. So we've got these guys right here. And here's what we're trying to do is, now keep in mind the wheel on the floor, touching the floor looks like this, right? And this is important because this changes the vector at which we're focused on. So as I'm going here, this direction, let me slide this over here just a little bit. As I'm going off to the left, what we're looking at, what we're concerned about is our right front value. So this guy right here, because it's rotating, and in this case, we have it rotating, we're checking to see if it's rotating greater than the initialized value. So that means that it's going to be rotating this direction right here. So because your gyroscope is going to be turning. And so then what we're going to end up doing is we're going to be adjusting the value on this guy to bring this, we're going to add some more power to bring this guy down, and we're going to reduce the power on this guy so this has less power. So it should actually force this guy with more power here and less power here. So we're minus here, plus here, should force this thing to actually rotate back this direction. And we're doing the same thing to this guy right here, right? So we'll add here and we'll subtract there, and it's going to adjust the wheels so that we have the rotation we need to make the correction as we're going along here. Okay, so once we have this though, now what we've got is we essentially have this put together to check the opposite direction. And that is, so I'm going to copy and paste that, and I'm going to say this is less than. And if that's the case, then we're just going to do the opposite functions on these. We're going to add these guys right here. Okay, so, and by the way, we want to change this as well because I adjusted that. And I mentioned that as part of the troubleshooting, we want to add some information here so that when we're looking at the screen, we actually can tell what adjustment it's making. So we're going to update our action string. And in this particular case, we're going to say, we're just going to copy this information in right here, right? So this will be fine because this will tell us which one we're actually looking at. So I'm going to cut and paste that in just like that. And then I'm going to, you know what, there's some information missing there. Let's do this differently. So we're going to say heading is greater than 180. And let's also say this right here so that this is useful whenever we look at it, because there's two options, two possibilities that it could be working through. So let's just take this whole thing. Now let's adjust this right down here. I'm going to paste this in. And then in this case, we'll be doing this adjustment. So what I want to be able to do is I want to be able to look at our screen on our phone that we're holding, and I want to be able to see, hey, is this making the adjustment in the right direction? Does it know the heading is greater than 180 degrees? And is it adjusting for less than or greater than from the initialized value? Okay, so that'll help us be able to figure that out pretty easily. So this is going to be our corrections. Now, again, we got to test this and make sure we didn't mess up any of the math, but this should all be good. The next thing we're going to do is, sorry, deleting stuff, didn't mean to, is let's take this whole thing now and copy it, because we're going to do essentially the same functions, but we're going to do it for going less than 180 degrees. And this will be 0. So greater than 0. And in fact, it probably, just to make a little bit more sense, probably makes sense to put the heading 0 between 0 and 180 degrees in order. So just so it's cleaner to look at. And we've already got our, just looking back here, we've already got our corrections already calculated. And we did that based on the fact that the current Z and init Z were not the same. So now let's just figure out our two use cases here. And this is just going to be a matter of making sure our values are correct. And I'm thinking that maybe I got these wrong. I'm looking at my notes here, and I did actually get these wrong. So let's fix this so that we have this correct. What we're doing here is this should be actually negative. This should be positive, and that should be positive, and that should be negative. And the same is true here. This should be positive, and this should be negative. So I had those values wrong. And okay, so then the other thing we want to do is down here, we're going to adjust these values, right? So this value is going to be actually positive, and this is going to be negative. And this one's going to be negative, negative, positive. Okay, so let's go back and talk about that real quickly. So in order for this to work, you have to, what's happening is the robot is rotating. And so what we're doing is we're actually making adjustments to the wheels so that it will force the robot to rotate back in its location, original position. And so in order to get the robot to rotate, you have to adjust, if you think about the way that the robot rotates, if it was just sitting in position, if I reverse rotate one side and forward rotate the other side, then it's going to rotate that direction. If I go spin the wheels the other direction, it's going to rotate that way. So really what we're trying to do is we're making an adjustment for that rotation while we're strafing across one direction or the other. And so that's where this gets a little confusing and is a little bit challenging. And so these values, they should be correct. I did actually test them on the robot and they worked out. So we'll go ahead and move forward there. I want to try to make sure I don't use up too much of your time. So I'm trying to be very cautious about time here. So let's also take a look at the situation where the heading is 0. Now, the reason why this is a special case is that all the wheels are rotating in the same direction. Whereas in our other scenarios, the wheels might be rotating in different directions. These are all rotating in the same direction. So anyway, what we're going to do is we are going to consider that case. So let's start with if heading equals 0. This will be the special case, and let's say end of if heading equals 0. Okay. So, and quite frankly, we're doing the same thing here, right? So this one is, in this case, it's actually, in my opinion, so much easier to think about. And that's part of the reason why I break it out separately. But in this case, you're doing, so if z int is greater than the initialize, which means that it's rotating to the right, then we need to put more power on the left. So the left is going to be positive, and we need to put less power on the right, right? So I'm sorry, if it's rotating to the right, I got that backwards. That's plus, minus, minus, and plus. You need to put more, if it's rotating to the right, you got to put more power on the right. On this side right here, you got to put more power. So we're going to increase the power on that side. But one of the things that makes this complicated is that normally that's the way it would be, but because I'm using a negative value on the gyro sensor, everything is actually inverted. So this is going to be negative, this will be positive, this will be positive, and this will be negative. And then we'll just reverse that for the next one, negative, negative, and positive. Yep. So we're just reversing that on the other side. Now, by the way, this is heading equal to 0, and current greater than, and this is heading equal to 0. Now, did I update these? I did not. So we want to make sure that these are updated. Otherwise, our notes won't be very good on the screen when they come up. And by the way, we did not, sorry, yes, that is correct. So heading less than 180. You could do that a different way if that gets confusing for you, but that's just there so that whenever we print out, go down and print this out, it's going to print that action value, let you know exactly what you're looking at, where the calculations are coming from, and you can figure it out pretty quickly. So that one's done. Now, the last thing we want to do is we want to take this guy and copy it, and we're going to set this equal to 180. So heading equals 180. So now we're going backwards, and we're going to consider the cases for it going backwards. And you could actually combine these with this up here if you wanted to, if you want to put the logic in place. So going backwards, this should be exactly opposite because you have the opposite problems. Let's reverse this. Let's reverse this. And there you go. So now we should have, now let's see, did I mess this up? End of if heading equals 0. Yeah, see, this is exactly why I do this. Huh, starting to get errors because I've messed up my squigglies. So let's get my squigglies put back in the right place. So this right here. Heading equals 0 goes here. Okay, so notice I missed that, but because I commented it in there, then it's helpful for me to troubleshoot. And then where's the, see, this one's out of place here too. So that's current Z. Which one was that? Current Z not equal to init Z. All right, so let's go back up and look at this. Current Z, this guy right here, should be right here. But the problem is I'm missing my squiggly here, which is the this is an excellent example of why I put these comments in here to figure out are my squigglies out of place. So end of if, and then it's this one right here. Okay, so you can see how I screwed that up, how easy it is to do. Now these errors that I was having up here should all be gone. So let's just make sure that this guy right here, this bracket is popping up with the right bracket. Does appear to be end of heading greater than 180. Is this one popping up with the right one? Does appear to be. Is this one popping up with the right one? End of 0. And is this one popping up with the right one? Yes. So this one right here is current Z. Yep. So that's all good. So now I fix those. Thank goodness. But again, I've been saying all along, it's so easy to mess those up. So you want to be careful about that. So one of the things that we're going to run into here that you should be aware of is that anytime I'm adding, like if you, let's say, let's do a quick case and think about what happens if somebody sends 100% power. Well, 100% power is 1. And I'm going to do some math on this, and this should never go above 1 because we assumed a unit circle in the way that we did that. So that should all be never go above 1. But let's say we've got a scenario where we are drifting and we're adding power to a motor that's already set at 1. Well, that's actually not good. We don't really want to do that. We want to clip those values so that they're never too high. And too high is either above 1 or less than -1 if you're doing negative power. So let me put a comment in here. And what we're going to do on this one is we are going to clip or actually, let's call it limit. Limit the value of the motors, let's be specific, drive motors, so that the power does not exceed 100%. Okay? Is that good? So the way this is going to work is we're going to say if, and we'll do RF, so right front motor is greater than 1, then let's just set the right front motor equal to 1. Else, if right front motor is less than -1, then set right front equal to -1. Okay, so that's what we're going to do. We're going to do that for all 4 of our motors. So we got the right front. Now let's do the left front. And I'm just going to change these out. Left front, left front, left front. Okay. Now let's do this again. We'll do this for left rear. It's going to be left rear. And this will be left rear. Okay. And then the last thing we're going to do is right rear. So we can do right rear, right rear, right rear, and right rear. Very good. So that's all of those. All right. So now what that's going to do is that's just going to clip the value. Now we haven't actually applied the power to the motor. That gets done down here, but we could set this up as a function like we did motors halt. We could create one called power motors, but I'm not going to do that. I'm just going to leave it as it is for now, and we'll go from there. So with this, we should end up with a program or a library that is going to strafe any direction we tell it. We give it a heading, it's going to go that direction. and it's going to autocorrect. At least that's the hope. So we'll need to test this. So the next step of what we're doing here is we are going to create a real quick autonomous mode program. So let me do a new Java class, and we can call this one test auto. Okay. And in test auto, we have to do a few things. We got op mode. Test auto, first of all, is going to extend linear op mode. So capital L, linear op mode. Yep. All right. And then in addition to this, we're going to have to add some lines up here. So the first thing we're going to do is we're going to tell this it's going to be an autonomous. And let's give it a name. Sorry, name equals, and let's just call it test autonomous. And we're going to give this a group, and we'll call it programming class. Okay. And I'm going to add another one here. I'm going to add disabled, but we're actually going to comment this out. We're not going to worry about that right now. Now we're going to need some other things, but we're going to get those. Those will be added here in just a second. So we'll just go with this for now. So let me create our robot. So let's create an object for a robot. We're going to do this as final static, and it's going to be hardware profile. You'll notice it just added our hardware profile class in up here. So hardware profile, and let's call this robot, and this equal to new hardware profile. Okay, so that's our constructor. And then we're going to do private linear op. Ooh, that's not what I wanted. Let's try that again. Linear op mode, and we're going to say op mode equals this for this class. And then we're going to do create a constructor, not that we need to, but public, and this is going to be auto. Sorry, what do we call this? Test auto. And then we're not actually going to put anything in here, but let's just do this as end of test auto constructor, right? And then what we're going to do is we're going to do public void, and we're going to do run op mode. Okay. Let's just do this as, because you saw me, I get these mixed up sometimes. End of run op mode constructor. All righty. So now let's build this. Let's start with, let's give a message to the user to let them know that nothing's ready. So we're going to do a telemetry, add data, and we're going to say robot state equals, and we can do whatever we want to. We can say not, oops, hang on. We can say not ready. Okay, because then what we want to do is we want to initialize everything. You know, have time to initialize it. So then we'll do telemetry dot update. Let's just print that to the screens. First thing we did is say we're not ready. So now let's do this. Let's add some comments here. What we want to do is we want to set up the initial state of the robot. And what we're going to do here is we're just going to do robot.init and hardware map. So it's going to initialize our robot. Okay, and then let's initialize the drive class. So we just built that whole drive class, Mecanum Drive class function. Let's use it. So we're going to do drive Mecanum. We're going to call this drive, and we're going to say new drive Mecanum, and we want to send robot and op mode. So it's using our op mode and our robot that we just initialized. So we just initialized that information. We're just passing that along. It's going to use the same information. And then the next thing we want to do, now that we've got the robot defined, is let's go ahead and calibrate slash initialize the gyro sensor. Now, I have always done this in the past. We're not actually going to do this right now. Well, maybe yeah, actually we can do this right now, I think. Well, we actually aren't going to be doing a calibration on this. We're just going to send some message to the screen here. So let's do, not that, sorry. Telemetry.add data, and we're going to say, let's provide the Z value. And so what we're going to do here, we're going to grab that Z value from just the initialized value directly. We're not going to, well, should actually be able to, let's try this. What do we call the function? Get Z angle? Yeah, I think this will work. So we'll try it. We'll try it this way rather than just calling the value. And we're going to do telemetry.add data. And we're not actually initializing. I don't want to confuse you guys. We're not initializing the gyro sensor here. I normally have done that with the modern robotics. And so I leave a space in there for it, but I don't think I've not found that I've needed to do that with the integrated gyro sensor that's in our controller. So this is the controller that we're using, the Rev expansion hub, and it has a built-in gyro sensor. And so whichever direction it rotates. And by the way, that's another reason why you do the function, the get Z angle function, is if you depending on how you orient that, you may want to make adjustments to the way that's set up. But anyway, the point is we don't have to worry about that right now. So what we're going to do is we're just going to update the robot state, or update the user on the robot state. And we're going to say the robot state is, let's just do initialized like that. Okay. And then let's send that telemetry.update and call that good. All right, so then the next thing we need to do is we just need to wait for the user to press the start button. And once that happens, then we can run through a function. Now, what I'm going to do is we're going to check. We always want to check to see if the op mode is active. So I'm going to do that as part of our function here. And then let me do this as end of if op mode is active. Okay. And that way we've got, we're going to put our test code in here for now. We're not doing anything fancy with this autonomous mode programming. And then once this is done, we're going to do a request op mode stop. So it's going to do whatever we tell it to do here, and then we're going to ask it to stop, and then it'll be good. So what we're going to do in order to call this is we're going to use our drive class that we put together. So we're going to say drive dot robot correct, right? That was a method that we created. And now it wants to know what power. So let's not go too crazy with power. So 20% power or 0.2 heading. And we can test all sorts of directions here, but we can try 90 degrees because 90 degrees is kind of interesting. 0 degrees isn't particularly interesting, but you could do that. And then we're going to set the duration, and we might set the duration to 10 seconds, right? So it should be in seconds. And then what we're going to do is, I know we put this in the robot correct method. It tells it to stop. We're going to put another one in there just to be on the safe side. So this is going to run for 10 seconds. Now, keep in mind, we could do this. We could say run 90 degrees for 10 seconds and then run to 70 degrees for another 10 seconds. So it strays one direction and strays back the other way, right? And we see theoretically it should end up right back where it started. So if we want to do that, we could do that. But the point is that we can put all of our test code in here and adjust these numbers however we want to adjust them, and go through all of the scenarios and bump the robot and make sure it's going to correct everything and see how it's working. All right, so I'm going to stop there, and we're going to call that good for today, because this actually has gone a lot longer than I wanted it to. I was trying to keep it short, which is the reason why I kind of abbreviated some things. But I'm going to stop it here, and then we're going to pick up with class next time. I'll talk to you guys later.